Welcome to problem solving session for Introduction to Group Theory. I'm Siddhi Balu Ambore from IIT Gandhinagar, and today we will discuss syllabus of week 10, problems related to syllabus from week 10, that is problems related to Sylow's theorem, application of Sylow's theorem, semi-direct product, and automorphism of groups. Okay, so let us start with our first question. So, question 1, that what is the order of a two Sylow subgroup of the symmetric group S4. Okay, and options are, first is 2 power 4, 2 power 3, 2 square, and D is 2. So this is the question which they have asked, and we have to answer this. So the questions ask us the order of two Sylow subgroup. So before going to the answer to the question, let us first discuss the statement of Sylow. So there are three Sylow's theorem. First, Sylow's first theorem, Sylow's second theorem, and Sylow's third theorem. So let us discuss all three of them. Let us at least go through the statements of those, because throughout this uh, session we will be using them multiple times. So let us first go through them. So Sylow's first theorem. Okay, so it is that let G be a finite group of order p power nm, where p greater than equal to 2 is a prime number and nm are natural numbers, such that GCD of p power nm is 1. This is the given condition for on G, on order of G. Then if this happens, then there exists a subgroup of order subgroup H of G of order p power n. And this H is then called Sylow P subgroup of this group G. So this theorem gives us the existence of Sylow P subgroup. And so what it says is that when we say that GCD of P power, so they are saying that order of G. So order of G is P power nm, and GCD of P comma n, P power n comma m is 1. This is the condition. So when we say that, it means that n here is the maximum number such that p power n divides my order of group. So when I write this, it means that we have a subgroup of order p power n such that we will have a subgroup of that order. So, and such that p power n that n is maximum in that case. So that's the existence of subgroup of order p power n, and that subgroup is then called Sylow p subgroup, and that's what Sylow's first theorem gives us. And then second theorem is Sylow's second theorem. Okay, and it again says that let G be a finite group of order p power n m, where again p n m are as in, or let me just write, where p greater than equal to 2 is a prime number and m belongs to n, and GCD of p power n comma m is 1. Okay, and let h and k be two Sylow p subgroup of G, then they are conjugate in G. So when we say they are conjugate in G, it means that there exists a element G in G such that K is equal to GHG inverse. So this is Sylow's second theorem. So it talks about, it gives us information about two Sylow P subgroups. So what it says that if I have two Sylow P subgroups with in group G, then they are conjugate of each other. And what does it mean when I say conjugate of each other? It means this. Okay, that this K, if H and K are two Sylow P subgroups, then this K is conjugate of this H. That is, K is GHG inverse for some G in group G. Okay, and that's what we have here so far in second statement. And third one is again Sylow's third theorem. It says that let G be a finite group of order p power n m, and again where p greater than equal to 2 is a prime number and m are just non-negative integers or natural numbers. GCD of p power n and m is 1, and let T be the number of Sylow P subgroups of G. Then first is that T divides the order of G, and second is that T is congruent to 1 mod P. Okay, so this gives us information about the number of Sylow P subgroups in given group G. So first theorem, Sylow's first theorem gave us existence of Sylow P subgroups. Second theorem talks about what is the relation between two Sylow P subgroups. And third one gives us information about the number of Sylow P subgroups we have in group G. So what that statement says that if T is a number of Sylow P subgroups in my group G, then T will divide my order of G and T will be congruent to 1 mod P in this case. Okay, so this is the information we have for our Sylow's theorems. And now we are going back to this statement. Like they are asking that what is the order of two Sylow subgroup of symmetric group S4. So S4, what is cardinality of S4? In general, we know that cardinality of Sn is n factorial, right? So uh, so cardinality of S4 is 4 factorial, that is 24. Okay. And it is, if I want to, so they are asking us the question asked about Sylow 2 subgroups, right? So when I am asked about Sylow 2 subgroups, then in Sylow's first theorem, when I talk about Sylow P subgroups, I need to have GCD of P power nm as 1. So let us write this 24 as power of 2 into some integer. Okay, so if I want to write that, though this is 2 square, 2 cube into 3, right? So this is 8 into 3, that is 2 cube into 3. Okay, so this is the information we have. And the moment I have this, then and GCD of, so I have G, that is S4, such that cardinality of G is 2 cube into 3, and GCD of 2 cube and 3 is 1. Then by Sylow's first theorem, we have that there exists a subgroup of order 2 cube in G. Okay, so therefore, here the order of Sylow 2 subgroup in S4 is 2 cube. Okay, so I hope this is easy to understand. When you are asked, so the correct answer is this 2 cube. Okay, so when you are asked to find the order of Sylow P subgroup in group G, what you need to do is you have to express the order of G in this form, and the moment you have it in this form, the order of Sylow P subgroup will be this P power n. Okay, so that's what this question was asking. So I hope this is clear. Okay, and let us move to now second question. So second question is, yeah. I hope this was clear. And question 2, which of the following is true? Okay, so A is semi-direct product of two cyclic groups is cyclic. B is direct product of two cyclic group is cyclic. C, direct product of two abelian groups is abelian. And D, semi-direct product of two abelian groups need not be abelian. So if you do not know, so direct product, we know how to, so direct product are of two types, inner direct product and direct product. So inner direct product, we just multiply two normal subgroups in group G. Okay, and semi-direct product is again a product of two elements in a group. Uh, product of two subgroups in a group G when one of them is not a normal subgroup. Okay, so in usual direct product, we need both the subgroups to be normal. Okay, so let us start with the semi-direct product of two cyclic groups, whether it's cyclic or not. So see, this is the question where first understand what the question asks. What the question asking is that semi-direct product of two cyclic group is cyclic, then direct product of two cyclic group is cyclic, then direct product of two abelian group is abelian, and the last one is semi-direct product of two abelian group need not be abelian. So if we are saying that something is true or something is false, wait, what's the question? Direct of two? Yeah, I brought to abelian group. This question is not like this. Need not be. I mean, even if we keep, wait, let us keep this whatever it is. Okay, and we will check which of the following is are true. Doesn't matter. Okay, so this is the question. So if we are saying that something is false, we have to give the counterexample. And if we think something is true, then we have to give the proof of it. So first statement is that semi-direct product of two groups is a cyclic. And so if we want to talk about semi-direct product, we have to go to a group where we have two subgroups. One of them is normal, other one is not. And we have to look at its product. And so we have to start with the subgroups which are cyclic. And then we have to prove that their product is not cyclic or whatever we get. So in general, before going to semi-direct product, first understand this one. What we get when we talk about direct product of two cyclic groups, because semi-direct, direct product is something which we understand better. So let us deal with the questions related to direct product first, and then we will go to one with the semi-direct product. So this first question is that direct product of two cyclic group is a cyclic. So let us understand this. So is this always true? Direct product of two cyclic group is always cyclic. And we have seen this even before, right? So for example, since we want to talk about direct product would be of any two groups. We do not need to have a well-defined product when we want to talk about just direct product of two groups. Okay. Uh, so I hope you remember how direct product. So if G1 and G2 are groups, then direct product of G1, G2 is just collection of all those A comma B such that A belongs to G1 and B belongs to G2. Okay, so this is uh, what we have in direct product. And the multiplication, so if A comma B, if A comma B and C comma D belongs to this G1 comma G2, sorry, G1 cross G2, that is direct product of G1, G2, then this new product in this G1, G2 is product of this A, B and, sorry, A star C and B star D, where this is multiplication in G1 and this is, sorry for that, multiplication in G2. Okay, so this is the direct product. So we have to start with the two cyclic groups. So which are the cyclic groups which we understand very easily? So those are cyclic group. The cyclic groups which we are most familiar are of the form Zn. Okay, so if we take, so let us consider, let G1 be Z2 and G2 be, let us take again Z2. Okay, then what is G1 cross G2? It is all those A comma B such that A and B both belongs to Z2. Since G1, G2 both are same, this is again with respect to addition. Okay, so this is our group G1 cross G2. This is direct product. And what is cardinality of this G1 cross G2? Cardinality of G1 cross G2 is this cardinality of this Cartesian product, that is 2 into 2, that is 4. So if I want to say that this G1 cross G2, this new G, if this G, that is G1 cross G2, is cyclic group, then there exists an element of order element X in G such that order of X is 4, right? That's what it will mean when we say that G is a cyclic subgroup. And uh, But if we look at every element, so any element but any a comma b, if I take in this g1 cross g2, then this a comma b, if I take this a comma b plus a comma b, then this is a bar plus a bar and b bar plus b bar, right? A comma b in G1, G2 means it will be of this form since we are in Z, or let me just explicitly write Z2 cross Z2. Okay. Then this will be 2a bar and this is 0 bar comma 0 bar. So therefore order of any a comma b bar is less than equal to 2. Right. I'm not declaring anything about what is the order of group, but if at all there is any order, then it will be less than equal to 2. That's what we are getting from here. Uh, So given any element in this G here, that is Z2 cross Z2, order of every element is less than equal to 2. But if my this G was group of, if it was a cyclic group of order 4, then there must exist some element of order 4 in G. But that is not possible because every element has order less than equal to 2. So since order of G is 4 and every element in G has order less than or equal to 2, less than equal to 2. Hence, G is thus, hence, as G is not a cyclic group. Okay, so I hope you understood what I'm trying to say here. Therefore, this statement that direct product of two cyclic group is always cyclic is not true. I mean, you can check this. I mean, we have discussed this earlier as well. And if so, this is not true, in fact. Okay, and if you want to go even further, understand that if order of G, if G is cyclic group of order n and G2 is cyclic group of order m, then G1 cross G2 is cyclic group if and only if GCD of m comma n is 1. Okay, and if you do not know, then if you understand, then try to prove this. Okay, here when we said this, the order of G1 and G2, GCD of order of G1 and G2 was 2 here. And instead of Z2, you could have take any multiple of 2 as a G2. I mean, Zn, where n is a multiple of 2. That group will again will have size 2 into n. But every element in the group, this new group G, that is Z2 cross Zn, where n is a multiple of 2, will have order maximum 2n. You can observe that. You can you can verify that. And when we have that, it will give us that this Zn cross Z2 or Z2 cross Zn is not a cyclic subgroup. Okay, so I hope that is clear. And now let's move to the second question. Say this C part. C part says that direct product of two abelian group is abelian. We have to check this. Okay, and as I said that if G1 and G2 are groups, then let me write this G1 comma star and B2 groups, and G is G1 cross G2, direct product of G1 G2. Then let A comma B belong to this G1 G2 and or C comma and C comma D belongs to this G1 cross G2 or G. Then we have to check whether this AB into CD, whether this is equal to or not, product of CD into AB or not. We have to check. Okay, but understand that this AB into CD is what? This is AB comma CD, where this AB is in G1 and CD is in where AB, or let me write here, where AB is in G1 and CD is in, I think I made a mistake here. This is AC, this is BD. Okay. But since G1 to abelian groups, since G1 and G2 are abelian, this implies that this AC is equal to CA and BD is equal to DB. So this implies my this AB into CD, which was AC comma BD. Each entry I can write it as CA into DB using this information which I have here. And then I can just, by the definition of product defined in my new G, which is direct product of G1 and G2, it becomes, so this implies that for any product, any element, any two elements in G1, G2, G1 cross G2, they commute. So therefore we get that. Therefore G1 cross G2 is abelian. The abelian property or the commutativity of G1 cross G2 is uh, uh, we got that because of the commutativity at each component of G1 cross G2. Okay, so therefore this statement that direct product of two abelian group is abelian is true. Now let us go to this first part, which we are yet to understand. So yeah, the A part. Let me start it. Yeah, that semi-direct product of two cyclic group is cyclic. In order to have that, we have to start with the two cyclic groups and we have to come up with the group which is direct semi-direct product of two cyclic groups, and but it is not cyclic. So let me give you that this statement is false. Semi-direct product of two cyclic group need not be cyclic. Okay, that's that because we just saw that cyclic direct product of cyclic group was not even cyclic. Okay, so let us, so we have to come up with some example. Sorry, sorry. So we have to come up with example of a group G such that we have two subgroups and which are cyclic, but their direct product, sorry, their semi-direct product is not cyclic. So one of them, in order to have semi-direct product, we we need one of the groups to be non-normal in G. Okay, so let G belongs to, let G be S3. Okay, and G has, okay, and let H is equal to this subgroup generated by transposition 1, 2, and N is subgroup generated by this cyclic group 1, 2, 3. Sorry, this cycle 1, 2, 3. Okay, and you can see that, okay, let me just write here. So this is just this group, and this is 1, 1, 2, 3. You can check this, and 1, 3, 2. Yes, yes. Okay, and let us, so we know that, so let us check which one of this is normal and the other one is not. So if I check, to check, so H, so let G belongs to G, and if you do not even want to do any of this, we, I mean, you can just go with the normal definitions which we have for, I mean, to check that, to check how to check in general the definition that a group G, a group, a subgroup H is called normal if for all G in G, G inverse is a subset of H again. Okay, so either we can go by this traditional method of checking whether a group H is, I mean, this is in G, or we can use this theorem which, or result which we also used in last class, that let G be a group and H be a subgroup of index P in G, and they are saying that if P is the least, P is the smallest, we use this theorem, P is the smallest prime number dividing order of G, then H is normal in G. So here when we have this H and N, then we know that order of H is 2, order of N is 3, and if I, and the least prime order of G is 6, and the least prime which divides order of G is 2 here. Okay, so if I choose, so if we then by above theorem, we will have that N is a normal subgroup of G, right? Since why? Because if I take index of G to N, it is 6 by 3, which is 2, and this is my least prime, that is dividing order of G. So therefore, by above theorem, let me write it. Since okay, so that will give me directly that this N is a normal subgroup in G. And to see that H is not a normal subgroup in G, let us choose two elements. So wait, yeah, let 1 comma 2 in we in G and 2 comma 3 in in H and 2 comma 3 in G. Then inverse, let us see. Okay, even I am not sure whether this will work, but what is product of this? This is 1 goes to 2 and here 2 goes to 1. So I am getting 1 here. 2 goes to 3, 3 goes to 3 here, and 3 goes to 2 and 2 goes to wait 1 goes to 2, 2 goes to 1, 2 goes to 3, 3 goes to 3, 3 goes to 2, 2 goes to 1. There is some problem here. Let me write this 1, 2, 3. So here 1 goes to 1. Yeah, here 1 was going to 1, and here 1 goes to 2, and here 2 goes to 3, 3 goes to 3, and 3 goes to 2, and 2 goes to 1. And this whole thing, I need to multiply it with this here. Okay, and we get now, let us check whether what we get here. 1 goes to 2, 2 goes to 3. And the moment I have this does not belong to my H, right? Or let me just write this completely. 2 goes to 3, goes to 2, and here. So this is 1, 3, which does not belong to my H. Okay, so therefore, H is not a normal subgroup in S4. So therefore, if I take this Hn, this is semi-direct product in G. And now we have to check whether the product form. So if I call this some G dash, so G dash, which is product of these two normal and non-normal subgroup, we have to check whether this is cyclic or not. And note that these two both of these are cyclic of order 2 and 3. Okay, but note that H and N are both are subgroups in G of order 2 and 3. Okay, so my claim is that this H into N is whole of G. Okay, and how to get that? So note that H into N has all the elements. So H into N contains H and N. So the only element which we need to show inside uh, this So we need to show. So that is we have 1, 2, this, and 1, 2, 3, and 1, 3, 2 in Hn. And now we need to show, so remain to show that 1, 3 and 2, 3 belongs to this Hn. And how to obtain that? So we need to choose one element from, so this is 1, 2, 3, 1, 3, 2, sorry. This is from Hn and N, and let us take, I need something to produce 1 and 3. So 1, 2, 3, I need only this. I only have this element here, 2, 1 and 3. And it will give me 1, 2, 1, and this will give me 3, 2. Hopefully 2 goes to, no. 1 goes to 2, 2 goes to 1, 2 goes to 3, 3 goes to 3, and 3 goes to 1, 1 goes to 2. Yeah, this is correct. And this is my 2, 3, which belongs to my Hn. And similarly, if you can check that 1, 2, 3, 2, 1, 3, if I take this 3, 1, 2, this will give me that 1, 3 belongs to Hn. You can check this. You can see this, that 1 goes to 3, 3 going to 3. So 1 goes to 3, 2 will fix, 2 goes to 1, 1 goes to 2, 2 is fixed, and 3 will go to my 1 again. Okay, so this implies that this H into N is actually whole of G, because there are no other elements remained, because H, N are contained in G, but we just showed that all the elements of G are contained in Hn. Okay, so this imply my Hn is the whole group G, that is S3. But note that H and N both were cyclic groups, but S3 is definitely not a cyclic group, right? So therefore, this semi-direct product of two cyclic group need not be cyclic. So this is what we just checked here. Okay, so semi-direct product of two cyclic group is not cyclic. And now the next question they are asking is whether the semi-direct product of two abelian group is abelian or not. But note that when we considered H and N to be cyclic, they were also abelian subgroups in G, right? Every cyclic group is abelian. We have that with us. And we just saw that the semi-direct product of those two groups were S3. So we had this, so similar for D. Oh, let me just write here. D was that, D is that semi-direct product of two abelian group need not be abelian. This is the question. So when they are saying need not be abelian, so it's okay to show just one example where semi-direct product of two abelian group is not abelian. But we can we can choose G to be S3 again. H was my 1, 2, N was 1, this generated by 1, 2, and here it is generated by 1, 2, 3. We can take, and this is cyclic, hence abelian H. And again, this 1, 2, the subgroup in S3 generated by this cycle 1, 2, 3 is also abelian. Okay, but we just saw that by part A, we have that G is Hn. Okay, this is semi-direct product, and but this is not cyclic and neither and not abelian. Okay, so we just have this example that semi-direct product of two abelian group need not be abelian. Okay, need not be abelian. So need not means if we have one example, the statement is okay to go. Okay, so that was the last part. So this one is also true. So what we have from here is that semi-direct product of two cyclic groups is a cyclic, need not be cyclic. In fact, direct product of two cyclic group also need not be cyclic. Okay, but direct product of two abelian group is abelian. We proved that, and semi-direct product of two abelian group again need not be abelian. So this is the information we have. I mean, this was the information we need to understand from this question. And also, if you are going to give exam, make sure that uh, you know many examples beforehand for all the concepts which we have learned uh, throughout the course, because those can come handy in solving most of the problems there. So now the next question, that how many 5 silo subgroups does the group A5 have? Okay, and just a second. Okay. Okay, let us just, yeah. Option is 2. B, it is, just a second. Okay. How many silo 5 subgroups does this has? So option is 2, 5, C is 6, and D is 12. Okay, this is the question. So it is asking us about number of 5 silo subgroups in A5. Okay, and what is cardinality? So forget about the cardinality of A5, as yeah, we need cardinality of A5. So what is cardinality of A5? A5, cardinality of A5 is cardinality of S5 by 2. If you don't know, please know this. And so in general, cardinality of AN is cardinality of Sn by 2. Okay, and cardinality of Sn is 5 factorial by 2. So this is 5, 4 into 3. So this is 5 into 12. Okay, and the moment I have this, I have the existence of 5 Sylow subgroup using the first Sylow's first theorem. Okay, but now we are asked about the cardinality of, we are asked about how many Sylow 5 subgroups are there in A5. Okay, but we have this Sylow's third theorem, which gives us information about the, so let me just copy paste this there. And here. Okay, so this theorem says that if T is the number of Sylow P subgroups of G, then T divides order of G and T is congruent to 1 mod P here. So here this 2, 5. So this is 5 into 12. So all these numbers, so we have to check these two conditions. This T divides order of G and T divides 1 mod P. So here 2, 5, 6 and 12, all these divides order of P. So the only condition which we need to check here is whether this T here is congruent to 1 mod P or not. So here in this case, that is we need to check. This T is congruent to 1 mod 5 here. That is we need to check that whether this holds or not. This was the only thing which we need to do here. Okay, so if I take first option 2, then 2 congruent to 1 mod 5, is this possible? That means that 5 divides 1. So this is not possible. So 2 is not the correct answer. Now 5, whether 5 is congruent to 1 mod 5, that is 5 divides 4. And again, this is not true. So again, B is not the option. Now 6, let us check whether this holds. See that whether 6 congruent to 1 mod 5, whether this is true, right? 6 divides 5, sorry, 5 divides 5. And this is correct. So this could be the possibility. And D part is whether this 12 congruent to 1 mod 5, and that is 11, which anyway we know that 5 doesn't divide 11. So the only possible choice for T here is 6. Okay. So this is this was the only thing which was asked. So it was application of Sylow's third theorem which we just saw. So the number of 5 Sylow subgroups in A5 is 5 is 6. Is that okay? I mean, we did not do anything. We just checked this second condition here. Let me just highlight this. We just checked this. Check this condition. This condition for given options. Okay, that was the only thing which we did. Okay, and apart from that, there are many theorems which we will see maybe today or next week as we move ahead. That So yes, now let's move to question 8. Sorry, no, question 4. What is the order of group of automorphisms of the group Z10? This is the question. We have to find the order of group of automorphism of Z10. And one thing which we all have seen even before when we learned first about group of automorphisms in this course. Okay, and we know this result or theorem, whatever you want to call. We know this, that the automorphism group of Zn is or Zn, and it is sigma A such that A belongs to Un, where this sigma A is mapped from Zn to Zn such that M bar goes to M into A bar. These are the only possible. And so when they are asking us, if you do not know, you can check this. I mean, try to prove this. Okay, and we know that, so if I want to find the cardinality of ort Zn, then since it is sigma is such that A belongs to Un, this needs to be isomorphic to this group Un. So cardinality of Zn is cardinality of Un. Okay, and we know that cardinality of Un is phi of n. That is, if it is n into 1 minus 1 by p1, 1 minus 1 by pk, where n is equal to p1 power some a1 pk power ak. So this is the general information which we have about automorphism group of Zn. And so here we are asked about automorphism group of Z10 and Z. So in short, we need to find this. What is this number? Okay, so therefore ort of Z10 is U10, that is 10 into 1 by 2 and 1 minus 1 by 5. That is 10 into 4 by 10. That is just 4. So therefore number of therefore answer is 4. Okay, I hope this is clear. You can do this with any n. This is true for any given, for any Zn, and you can apply this to any cyclic group. Okay, so understand that, note that for any cyclic group of order n, we have cyclic group, let us call Cn of order. We have this Zn isomorphic to Cn. Okay, so therefore Hence, for any Cn, this is cyclic group of order n. By above result, we have cardinality of aught of this Cn is actually equal to Un. Because since these two groups are isomorphic, they are one and the we can consider them as same group. Everything which Cn satisfies, Zn satisfies, and vice versa. So therefore, automorphisms of Cn will cardinality of automorphism of Cn will also be Un, and in general this will also be true for cyclic group of order n. Okay, so I hope this is fine so far, and yes, next is yeah. Now this is next question. I hope this is fine. If not, please you can unmute and ask. Otherwise, we will move further. So this is the question. We have to check whether true or false. Any group of order 15 is cyclic. Okay, this is the question that is asked, and let us try to prove this with true or yeah. So we are asked whether any group of order 15 is cyclic or not. So either we have to generate a subgroup, sorry, we have to generate a group of order 15 and show that it is non-cyclic, or we have to prove for any group of order 15 that it will always be cyclic. Okay, so let me just give away this statement is actually true. Okay, so what we will do is we show that let G be a group of order 15, then G is cyclic. This is what we will show now. Okay, so note that since let G be a group of order 15, that is 3 into 5. Okay, so let N5 denote. So since it is 3 into 5, it has Sylow 3 subgroup and Sylow 5 subgroup. Okay, both. And let N5 denote the number of Sylow 5 subgroups of G. Okay, so then by Sylow's third theorem, we have this N5 congruent to 1, right? It is congruent to 1 mod 5. wait. Then this will imply that N5 is N5 is 5R plus 1 for some R. Okay, and we can choose this R to be, let me just, yeah. This implies this N by N5 is equal to NR plus minus 1. So we have this N5 congruent to 1 mod 5 and N5 divides 15, right? So this imply that, so from here I have this N5 is 5R minus 1 for some R positive, and yeah, and this 5R minus 1 now divides 15 from the, this is just the application of Sylow's third theorem. And so if that has to happen, then the only possibility I have is N5 to be 1. Okay, I mean, here instead of plus, we can also choose plus. That won't matter. I mean, this is just convention. And we get that, yeah, this is correct. N5 minus 1 divides 5. So, yeah. So, this is, yeah, N5 is 5R plus 1. And yeah, that's how we will get that this. Yeah, okay. So, this implies that R needs to be 0, and the only possibility, therefore N5 needs to be 1. Okay, because if I have any N positive, then it will have 6 divides 15, which does not even hold. So the only possibility for R here is 0, and yeah, therefore we get that G has unique normal subgroup of order 5. And why this is normal subgroup here? Because we can use that theorem which we just used in earlier question, that if I have G such that and H is a subgroup of G such that index of G to H is P, where this P is the smallest prime, then that becomes the normal subgroup of G. Okay, so this imply that since H has cardinality 5, here, since here G colon H is 10 by 5, 3, which is smallest prime dividing order of G here. Okay, smallest prime. So therefore, we know that only subgroup of order 5. So 5 is the maximum number which divides order of G. So, 5 power 1 is the maximum power of 5 that divides. 1 is the maximum power of 5 which divides order of G. That's why the Sylow P subgroups are of order 5. Then we have that using this information here, using Sylow's third subgroup, we got that only there is unique subgroup of order 5 possible in G. And next we got the normal, that this group is normal using the theorem which we have used earlier as well. So there is only one group of order 5 in G that is normal in G. Okay, so if we follow the similar steps, we can prove that following, we can follow similar steps and prove that G has unique normal subgroup of order 3. So following the same similar argument here, that we can do Sylow 3 subgroup and so on, and we will get that the only subgroup possible is of order. Here also we will have 3 r plus 1 divides 15, and the only possible choice for r then will become 0, and 1 will be the only possibility for number of Sylow 3 subgroups in G. And for the uniqueness, we can so the only group of order 3 is possible, and for normality, we can go quotient by 3 and have a subgroup of order 5, which is cyclic and so on. And you can prove that it will be a normal subgroup in G and so on. Okay, so since H intersection K K is only identity, and both are subgroups of G, it follows that there exists a bijective homomorphism or one homomorphism from P H cross G, sorry, H cross K to G. Okay, and we just saw in earlier direct product that in this theorem you can, this follows. So this you can check. Okay, so there exists one homomorphism from H cross K to G. And once I have that, since H is generated by some X, we can choose, and K is generated by some Y, such that order of H is 3 and order of K is 5, then we know the order of this G cross K will be 15. And then there exists and we know that we just saw in earlier theorem that if G1 cross G2 if we have, and if GCD of order of G1 and G2 is 1, and if G1 and G2 are cyclic, then G1 cross G2 is also cyclic. So we got two normal subgroups in H and K, and we arrived at the conclusion that this H cross K 2G is group homomorphism. And since order of H and K, so this is cyclic by this argument using, this is cyclic using this argument. And since H cross K is isomorphic to G, we get that G is cyclic. Okay, and the element, the element which, the element which generates G is P of x comma y. Okay, because the here, since in H cross K, since H cross K is generated by x comma y, x is, H is generated by x and y, K is generated by y. You can check this. And this image of an order of this will be whole of G, because we are talking about isomorphism. So whatever order of element I have in domain, the same order will I have for its image in codomain. Okay, so that's how we proved that any group of order 15 is always cyclic. Okay, I hope this is okay so far. Okay, and one more. Similarly, I mean, you can also prove this for this also. Question, this is, I think, question 6, yeah. Question 6. And you can choose is that again true or false, or yeah, that let G be a group of order 119, then G is cyclic. And you, since G is 119, that is again 7 into 17, which we have here. What we can do is we can again follow the similar argument which we did for 15. We can start and then arrive at conclusion. I mean, let us see again here, like what we can do. We can follow the similar process, or what we can do is that let, so 17 divides order of G. So we have a Sylow 17 subgroup in G, and N17, that is, let N17 be number of Sylow 17 subgroup in G. And what we can do then is, then this N70 will divide 119, and N17 is of the form some 17R plus 1 or 17T plus 1. And again, this will imply that N17 is 1, because again this 17 divides 119 and it will divide 17T plus 1. So this will imply N17 divides 1 and so on. I mean, you can check, and this will imply that N17 is 1, and G has a unique normal Sylow 17 subgroup in G. And similarly, we can show that we have Sylow 7 subgroup. And again, we can, instead of using this homomorphism and other things, what we can do is, so this Sylow 7, and similarly, we can choose, we can prove that G has unique normal Sylow 7 subgroup in G. And since 17, say U and say W, then this U is generated by some X, and this W will be generated by some Y, right? These are Sylow subgroups in G of order prime. So they will be generated by some element of such that order of X is 17 and order of Y is 7. And then we can check that then order of this element XY will be what? This is 17 into 7, right? Because we know that a order of XY is order of X, order of Y by GCD of both the orders. If you do not know, please check. Okay, and since GCD of 17 and 7 is 1, we get that this is 119. And the order of my group is also 119. So we do not actually need to induce, invoke all this homomorphism and other thing. We can just prove that there are we have subgroups of order. So if I have group of order PQ, and I just proved that we have unique subgroup of order P, unique normal subgroup of order Q, then since both of them are cyclic, the product of their generator will be an element of order PQ because of their GCD, since their GCD is 1. And that element will now generate my whole group. And this will again give me that G is a cyclic group. So this is also true. Okay, and if so, does this always happen that if since we saw these two examples, that I had group of order PQ, and it turned out that they are cyclic. But does this always happen? Do we always have, if I have a group of order PQ, is it always cyclic? The answer is no, right? Because we already know that S3, the group of three permutations, is not a cyclic subgroup. It is again the cardinality of S3 is 2 into 3, but it is not a cyclic subgroup. So what is the condition which we need to have in order to say that, yeah, if this is happening, then my group will always be cyclic. So this is the statement which, let me write this as a theorem or result, whatever you want to call, that let G be a group of order PQ where P greater than Q are two primes. So we are just giving the notation, following this condition that P is greater than 2 without loss of generality. Then we say that then G is cyclic if Q does not divide P minus 1. This is the condition which we have, that G will be cyclic if Q does not divide P minus 1. In case of S3, in S3, cardinality of S3 was 6, which is 3 into 2. And here this is my P, this is Q. And 2 definitely divide this 3 minus 1. So that's why using this theorem, we can directly say that S3 is not a cyclic subgroup. Okay, and yeah, it follows from this theorem. And let us now quickly try to understand that using the applications of Sylow theorem, that how we can prove this theorem. Okay, and so let T be the number of Sylow P subgroups of G. Okay, so P was my greater prime among P and Q. And I'm saying that let T be the number of Sylow P subgroups of G. Okay, then by Sylow's third theorem, and also which we have proved, used a lot of time, that T will be some Kp plus 1, right? For some K greater than equal to 1. Okay, so my T will be some Kp plus 1, and T divides order of G, that is PQ. Okay, and then by above conclusion, so using this, what I have that P divides T minus 1, right? And wait, yeah, that is there. Then we can conclude that because see, this will be Kp plus 1 divides PQ. But so if that is the case, then this Kp plus 1 will divide Q or Kp plus 1 will divide P. So this will imply, since this is definitely not true, this is not true. And see if Kp plus 1, I mean, wait, Kp plus 1 cannot anyway divide Q because since if this K is greater than equal to 1, this Kp plus 1 dividing Q implies this is not true. Kp plus 1 cannot divide P again for any positive K. And second condition, Kp plus 1 dividing Q is again not possible because P is greater than Q. Then this Kp plus 1 will be something greater than P again. And that's why. So we can conclude that this K is 0. Understand that? Not possible if, so let me just write this. Kp Kp plus 1 dividing P is not possible if K greater than equal to 1. Similarly, Kp plus 1 dividing Q is not possible since P is greater than 1 for K greater than equal to 1. For K greater than equal to 1 as P is greater than Q. You can again check this and we will get that K is a 0. Hence, G has unique normal, we do not need normal, unique Sylow P subgroup in G. And say H, then again, then H is normal again. H is normal from the theorems which we are proving so far, which we have used so far. Let K be a Sylow Q subgroup of G generated by element Y. That is my K is, I can have, I'm not interested in knowing whether it is normal or not or other thing. I am just interested in knowing whether I just need existence of this Sylow Q subgroup. That's it. So it exists from theorem, Sylow's first theorem. And since it is subgroup of order Q, Q is prime, so I get that K is generated by some, it is cyclic and generated by subelement Y. And again, so this is just the existence of Sylow's theorem. So then I have, if this H is generated by K, K is again cyclic, K has odd, sorry, H is again a cyclic group because H has order prime. A- H is prime order group. So then this Yx Y inverse belongs to H, right? Because this is normal. So in H. And this implies this y inverse is some x power r for some 1 less than equal to r less than equal to p minus 1, right? This is okay, right? Because h is generated by x. So if this y inverse belongs to r, yes, wait, yes, okay. So the moment I have something of this form, that suppose if this is some I for some I in p minus 1. So, and again from this that y this I have, and also for any r, this y inverse power r is x power I power r, right? Because this, note that y y inverse is what? Is y. This two gets cancelled. This I get x power x square. No, no, no. Wait, wait. Says that after this we get, yeah, y power r x y inverse y power minus r is equal to x power I r. How is this happening? For some r in q. Is this true? Let us assume for now that this holds. If not, we will check this. For some r, and since for some r less than equal to q, and since y is, yeah, since y power q is 1 because y is generated by, so since K is a Sylow Q subgroup and K is generated by y power Q is 1. This implies that y power Q x y minus Q inverse is x power I power Q. This is x in this implies that x is equal to this is anyway x, so this imply x is equal to x power iq, and this will imply we will check that x power iq minus x is identity. Then by Lagrange theorem, I get that, yeah, iq minus 1, oops, this is minus 1, divides pq. Okay, or since this belongs to H, this also implies that IQ minus 1 divides P, or P divides IQ minus 1. Yeah, P divides IQ minus 1. Because order of X was P, and we have some power here of X which is dividing E. So I get P power IQ. We still need to check this, okay? We will do that later on. Yeah, but for now we have this IQ minus 1, and yeah. So our claim is that we claim this. So this implies that I power q is congruent to 1 mod p. And we claim now that this I is actually 1. Okay, so suppose not. So since p is a prime number, mm, this implies that, and since I power q is congruent to 1 mod p, this implies that GCD of I and p are 1. This is clear, right? This is clear. I mean, this please understand. This is basic number theory. I mean, not even number theory. This is otherwise this won't hold, because if GCD of I and P is not 1, then this does not make sense. Then it will imply that P divides 1. That's not possible. So this please understand. Okay, so since I power q congruent to 1 mod p, this GCD of I and p is 1. So this imply, and since I was between 1 and p, this implies that this I belongs to UP. Right? UP was all those K in P such that GCD of K and P is 1. So hence order, since I power q congruent to 1 mod p, this I power q, since q is the order of element I in this UP, right? because I power q is 1. So, but UP, order of UP is P minus 1 because ZP is, it is ZP minus 1 because everything has, I hope you know this, UP is, cardinality of UP is what? P into 1 minus 1 by P. That is just P minus 1. Okay, only possible primary expansion, primary decomposition, I mean, the prime power expansion of P is just P. And this is what we have. So cardinality of UP is P minus 1. And since I power Q is, I power Q is 1 and Q is less than P, this Q divides P minus 1. But this is contradiction because we have already assumed that Q does not divide P minus 1. So therefore, this I needs to be, therefore I is equal to 1 because we assume that here, suppose not. And therefore, we get that I is equal to 1. And the moment I have this I is equal to 1, here I get, therefore, since I is equal to 1, this implies xy is equal to yx because what I had there, xy, yx, y inverse was x power I, and this I get yx is equal to y inverse is equal to x. This implies yx is equal to xy, just multiplying by y from the right side. And then order of this xy will be pq, right? Because the formula which we need for, see, this formula which we apply, order of xy is equal to order of x, order of y by GCD of order of xy. This holds only when x and y commute. Okay, in general, this is not true. Okay, we can have elements in a group with finite order, and when we reverse the multiplication or the order of xy need not be, I mean, if xy is not equal to yx, then we can't, uh, then the elements will have very different order. And the moment I have xy is equal to yx, the order of xy becomes pq. And since cardinality of gq was pq, since cardinality of G is PQ, and we have element of order PQ in G, we get that G is this, G is cyclic generated by XY. Sorry. Element XY in G of order PQ in G. Okay, so this is we have so far. Now the only thing which we need to verify is this. Is this trivial? We have this. Because we have used it here when we raised q by power, here when we raised x by power q, So let us try to check this. So we have y x y inverse is equal to x power I, and we have to we claim that y power r y power r x y power minus r is equal to x power I r. This r is less than equal to q. How is this the case? Let us check. Okay, this, let us, y square x y square is what? This is y into x power I into y. So this is right, and this is what? Okay. So we got it. So what we have here is x power I r, and but x is, yeah. So this is y. Okay, now we did something right, which, but y power, this is x into, yeah, x into, I want to show that y square x y inverse square is x power I square, and I have y x y inverse. If I take this, this is what? Y into x power I y, right? Y inverse. I want to show that this is, any suggestions from anyone? How can we prove this? This is y square, because we still, I mean, if we just directly take product, what it will give us? I mean, let us leave this here for now, or I will just upload this in the notes, or if you can do this, check this, that we need to prove this from here, we need to get here. And how to do this? Please try, uh, prove this, because we have extensively used this to arrive at the conclusion where we said that it is the order of y here. I mean, we got this expression because of that. So we need to prove that. Okay, if you do not, I will either upload it in today's notes, or we can discuss it in next week or in upcoming, whenever we get that opportunity. Okay, so I hope this is okay. If you have any doubts, please let me know. But we still, because we are almost at time. Yeah, it's all, we are about time already. So if you have any, I mean, if we start the question now, it will take too much of time. If not, then let me just write this theorem, which might be useful for you in your assignment. Let me just write the statement only, not the entire, not the proof and other things. Yeah, this one. You can always use this theorem that if G is if G be a group of order PQR, where PQ and sorry R are distinct primes, then one of the Sylow subgroup of G is normal. Okay, so you can't actually directly use the previous theorem which we had, that since if I have a subgroup, when I take quotient, then H is R and so on. That won't help here. Uh, okay, so we need to actually construct, I mean, this is non-trivial. Okay, this statement is non-trivial and it extensively uses all the Sylow subgroups and Cauchy's theorem and whatnot. And you can arrive at this statement. I mean, you can try to prove this. You can try to prove, and and also you can use this in the assignment if you want to. If we get time, we can do this next class or next session or after that. Okay, if there are no more doubts, then we can. If there are no doubts, then we can stop here. If you have any doubt, please write it in the chat, or you can unmute and ask. And you can also raise them in the discussion forum. We will try to answer them. Okay, so if there are no further doubts, maybe we can stop. Thank you.